In this video, I'm going to teach you about Hooke's law. And Robert Hooke was an English physicist who studied elasticity and springs among many other scientific concepts. Hooke's law essentially states that the more a spring is extended or compressed, the greater the restoration force. Now, if you would, go ahead and get out your College Board equation sheet. Let's take a closer look at the equation for Hooke's law that you see highlighted on your screen. This equation states that the magnitude of the spring force is equal to the spring constant multiplied by the magnitude of the displacement of the spring. Now, let's break it down even more here. And again, please remember, we're referring to any elastic material. So we could be talking about a rubber band. We could be talking about a bow from a bow and arrow. The force of the spring is what I'm referring to in my definition as the restoring force or the restoration force. If you think about it, if I take a spring and extend it, and then I let go, the spring force will restore the spring back to its relaxed or equilibrium position. Now, K, I taught you about when we looked at elastic potential energy in a previous video. That is the spring proportionality constant. Lastly, we have the displacement of the spring or the material. That would be the extension or compression of the material. Now let's look at our units. So for the restoring force, obviously our units would be Newton. Please also recall that our units for the spring constant are newtons divided by meters. And lastly, for displacement, we will have meters. So to expound a little bit on what is meant by restoring force, this is basically saying that the spring or the material, when it is extended or compressed or deformed in any way, it will restore back to its equilibrium force. That is the direction, rather, of the force. So if I were to push a spring down and compress at a given distance and then let go, the restoration force is in the opposite direction of the compression. It was down. The force is now up. Many times you'll see Hooke's law written with a negative sign before the kx. Well, most of the time, I'm simply going to write it like this because I'm teaching you now that the spring force or elastic force is a restoring force. And that restoring force will be in the opposite direction of the displacement of the material anyways. So you just need to keep that in mind. Now, if we look at this graphically, it turns out that the slope of a force versus displacement graph for a spring is actually the spring constant K. Let's look again at the equation for Hooke's law, and let's talk about some of our proportionalities here. So the force of a spring is directly proportional to the displacement of the spring. In other words, if I wanted to double the restoring force, I could simply double the displacement of the spring, and that would result in 2 times the force. Likewise, the force of a spring is directly proportional to the spring constant K. Please remember, though, that K is a property of the material. So if you wanted to change the restoring force of a given material, you would actually, by manipulating K, you would actually need to change out the spring for something totally different, okay? So again, K is a property of the material. I want you to look at this video clip and this graph which shows the force as a function of displacement of the spring. As you can see, this force is increasing proportionally as the spring is extended, just as we talked about with the Hooke's law equation. So this force is increasing as a function of the displacement, resulting in a graph that has a constant positive slope, and the value of that slope would be the spring constant, K. Let's look at our units for slope. Let's look at Hooke's law. Let's rearrange Hooke's law to solve for K, which will enable us to look at the units for the spring constant. So dividing both sides of Hooke's law by x, or the displacement, we end up with force over displacement. If we now look at the units, we end up with newtons over meter. Now, throughout this course, I've implored you all to always just look at your units. You don't need to memorize that the slope of this is K. You could simply look at what are the units for rise over run for the slope. Oh, Newton meters, those are the units for the spring constant. That's what I want you to do. So let's look at these two values circled now on the graph, and let's go ahead and calculate the slope. So if we were to calculate the slope, which is the spring constant K, we would end up getting 40 newtons per meter. Now you can do that for any of the values on this graph, and you're going to get the same value because this has a constant slope. You're going to get 40 newtons per meter. So that's our spring constant, K. Next, I want to talk about the area under a force versus displacement graph, because that is actually equal to the work, or the spring potential energy. So now, go ahead and consider from a previous video our discussions of work. And it shouldn't be any surprise that work is actually going to result in spring potential energy. So if I do work to a spring and compress the spring, well, now that work has been transferred into spring potential energy. Okay, that's what this is basically stating. So keep that in mind. The area under a force displacement graph will give you the work, which will give you the spring potential energy. So let's go ahead and look at the graph and look at the energy associated when this spring is compressed a distance of 0.1 meter. You see we have a right-angled triangle. So we're going to use the formula to find the area of this right-angled triangle to be 1/2 base times the height. Now, if we plug in values, I'm showing you something here. If we plug in some values here for the x and the y axis, we have 1/2 x, okay, that's the displacement or the base of our right angle triangle, multiplied by the height, which is force. Now, remember what force we're talking about here. We're dealing with the force of a spring. Now remember the equation I just taught you about in this video for Hooke's law. The force of a spring is equal to K multiplied by X. So if we substitute that value into our equation like this, then we end up with the formula for spring potential energy, 1/2 K x squared. A lot of students say, when looking at this graph, I don't see how it equals spring potential energy when I'm doing, say, 1/2 base times height. In this case here, I'm showing you where that comes from. We're taking Hooke's law, we're expressing force in terms of the spring constant and the displacement of the spring, subbing that into our expression, and there you have it, 1/2 kx squared, which is the spring potential energy. So how much work is done to actually extend this spring 1/10 of a meter? Well, now we can figure that out because we know that the area under this graph, under this curve, will equal the spring potential energy, which is equal to the work. So let's just plug in values here. Let's extend it 1/10 of a meter, and our force required to extend it 1/10 of a meter is 4 newtons, which means the work that is done is equal to 2/10 of a joule. In this video, you guys, I've talked to you about looking at Hooke's law, graphically looking at the force as a function of displacement and understanding that that is the work that is done. And in the context of a spring or any elastic material, we're looking at the elastic potential energy when finding that area. Lastly, when you find the slope of a force versus displacement graph for a spring or any elastic material, you're finding the spring constant K. And I'll see you guys in class.